Okay, now we will go through the exemplar problems in the class 12 physics chapter 9 ray optics and optical instruments. Hmm. So I'll show you some basic things. If you take a plane mirror, okay, the image is formed due to the reflection. Okay, in the mirrors the image is formed due to the reflection. So it is formed on the back side of the mirror. Back side we have some silver coating something. So this is the mirror, plane mirror. Virtual image is formed on the behind the mirror. Okay, so now if you take a mirror and it is formed on the back side, then it is called virtual image. Okay, now the real image is formed in front of the mirror itself. So if you take a mirror like this, object and image, then this is the real image. So it is formed in front of the mirror. Okay, this is virtual, this is real. And here if a image is formed below the object, below the principal axis, that is the inverted image. It is inverted image. Object here, image here. So that is inverted image. Okay. Erect image means is not below the principal axis, above only, in the same same level as the object. This object here. Okay, not below the principal axis. This is the erect image. So real is same side. Now if you take a two medium, let's say air and a glass. Glass is denser than the air. So this is the normal to this surface. If light ray comes from this side and if there is no refraction, it will go straight in this path. Okay, so when the light travels from the denser to the rarer medium, it bends towards the this side, that is it bends away from the normal. So this is the normal, it bends away from the normal. Without refraction, this light will go in this direction, so it is going away from the normal. So when denser to rarer, away from the normal. Suppose this is air and this is glass, that is rarer to denser, then it goes towards the normal. Okay, so normal is the light ray, it will go straight in this. So refraction go towards the normal. Here towards the normal, this is away from the normal. Okay, when light goes from denser to rarer medium and it exceeds some angle, see at some angle the refraction will be along this surface. Okay, and when this refraction is along this surface, this incident angle is called the critical angle. Okay, when denser to rarer, away from the normal, light refracts away from the normal. So when you increase this incident angle, at some angle this angle of refraction is 90 degree. That angle is called the critical angle. Okay, the refractive index of the glass is around 1.5. Air is 1. Okay, so you can refractive index, they use n or mu symbol. Okay, so 1 by, this is the mirror formula, 1 by f focal length equal to 1 by u plus 1 by v. U is the object distance, v is the image distance. Okay, in mirror, image is formed by the reflection. So u is the object, v is the image. This is the lens formula. The difference between these two here is this minus sign only. Okay, so the lens image is formed by the refraction. Okay, the refraction on the both sides of the lens image can be formed. So you have to read about the sign conventions in the book. F is the focal length, U is the object distance, V is the image distance. This is the lens maker formula for the combined lenses. If you have two lenses combined into a single lens, so power equal to 1 by focal length, 1 by f equal, this is the formula, 1 by f equal n to 1, that is refractive index of the medium 2 with respect to 1. 1 by f equal to n2 minus 1 by 1 by r1. This 1 is nothing but the refractive index of the air. If there is some other medium, then this 1 has to be replaced with that number. Okay, let us say glass means it has replaced with the number. Okay, that is important. This 1 by f, 1 in this lens maker formula, these two ones are refractive index of the air. R1 is the radius of curvature of the lens 1. So that is normally right side. R2 is the left side. Okay, that is the negative sign. When f is positive means it is a converging lens, f negative is a diverging lens. So what is the difference between microscope and telescope? Okay, in the microscope, the focal length of the eyepiece is greater than the focal length of the objective. Okay, objective eyepiece. So this focal length eyepiece is greater than the focal length of objective, but for the telescope, that is other way. Focal length eyepiece less than this. Okay, is magnification factor, here magnification factor. The angular magnifier is d phi f. 1 plus d phi f is magnification, but angular magnification is d phi f. Okay. See, light has many colors, but the visible colors to the eye is 7. That is VIBGR: violet, indigo, blue, green, yellow, orange, red. Okay, red is the highest wavelength. This is the lowest wavelength. Okay, there is a Snell's law, sin I by sin R. Sin of incident angle by the refractive angle equal to the refractive index of the medium 2 with respect to 1. So you can use mu 2 1 or n 2 1. Refractive index of 2 with respect to 1. So how this refractive index is related to the velocity? So velocity of medium 1 divided by velocity of the mu 2 1. Okay. This is the velocity of the denser medium, is rarer medium. So is mu 2 1. Critical angle, I already told you, at the incident angle at which the refracted angle is 90 degree from denser to rarer medium light travels. Okay. So the velocity of light in water is less than the velocity of air. So the denser medium like water glass, the velocity of light is less than the velocity of air. So in the denser medium, n1 to 1 is denser, 2 is rarer. We have a relation between the refractive index and the critical angle. Refractive index equal to 1 by the sine of critical angle. N1 to 1 is the denser medium, 2 is the rarer medium, n is the refractive index. It is refractive index related to the real depth, and apparent depth is like this. Real depth divided by apparent depth is the refractive index. Okay, a ray of light incident angle theta on the refracting faces of the prism emerges from the other end normally. This is so. From the other face normally means the R2 will be 0 here. So I will show you what is R2 and R1. If the angle of the prism A is angle of the prism is 5 degree, A and the prism is made of material, the refractive index. Okay, the angle of incidence they are asking. See here, this is R1, this is R2. Okay, so emerges normally here means the R2 will be 0. That is emerges normally. Okay, on the other side. So from the book, R1 plus R2 equal to A, that is 5 degree is given. So R2 is 0 means R1 equal to 5. So I by r, incident by refraction angle, is equal to mu. So the angle of incidence is equal to mu into this is 7.5 degree. Okay. So here R1 plus R2 equal to A. Okay, this is the prism. Okay, this formula is given here. So this angle A equal R1 plus R2. So mu or n you can use for the refractive index symbol. A short pulse of white light. White lights have many colors. The visible color is only 7 color. Okay, from air to glass. Okay, in the normal incident. Normal incident means there will not be no bending, so it will pass through straight. After traveling through the slab, the first color to emerge is. See here, the important thing is that there won't be any frequency change when light travels from one medium to the other. Okay, there won't be any frequency change, but the velocity will change. Okay, velocity of light will change. Velocity of light will change. So it is light incident and normal incident means the incident angle 0, refraction angle also 0. So VGR R is the highest wavelength, V is the shortest wavelength. So the velocity of light is equal to frequency into wavelength. Okay, this wavelength is more for the red light, so this red will come out first. Okay, red will come out first. The normal incident means no bending of light. Okay, the object approaches a convergent lens. Convergent lens means convex lens from the left of the lens with the uniform speed and stops at the focus. The image, okay, the moves away from the lens. Okay, not this, moves away from the lens with the non-uniform acceleration. Okay, so you have to compute the image distance v for different u and then you can see. Okay, in the book there is one example related to this 7. Okay, so you can go through this. Suppose while sitting on a parked car, you notice a jogger approaching. Okay, this speed like this. So what you have to know, this is for the non-uniform acceleration. Okay, moves away from the lens with a non-uniform acceleration. That is what the result at various distance. In this distance, this distance, this distance they measured. Okay, so using this formula you see this image is at this, then for this distance image is this. Okay, so the after that this is the conclusion. Okay, so you read this. So it's this image moves with the non-uniform acceleration, moves away from the lens with non-uniform acceleration. A passenger in a aeroplane shall see the primary and the secondary rainbow as concentric circles because there is no reflection from the ground. Ahead of the ground there is no ground ahead of the passenger. So refraction and total internal reflection causes this rainbow. Okay, water to air. Water is a denser medium, air is the rarer medium. From water to air light travels, this causes this rainbow. So this will appear like a concentric circle. Okay, not arcs. Arcs will appear from the ground, not from the aeroplane. You are given 4 sources of light. Okay, each one provide the light of one single color, okay, red blue given. Suppose the angle of refraction for the beam of yellow light corresponding to the particular angle of incident at the interface is the angle of refraction 90 degree, mean that is the critical angle. Okay, what is critical angle? So that is the angle of incident for which refraction is 90 degree. So they are given the critical angle of yellow, the yellow light they are given. Angle of the yellow light they are given. Which of the following statement is correct if the source of the yellow light is replaced with the with that of the other lights without changing the angle of incidence? So angle of incidence is not going to change. Okay, so now they given the critical angle of the yellow. Okay, critical angle is directly proportional to the wavelength. Okay, wavelength more means critical angle will more. So yellow this is the yellow is already reached critical angle. So these critical angle of these four colors will be less than the critical angle of this color, because the critical angle is directly proportional to the wavelength. These wavelength are less than the yellow. Okay, so using that concept we should approach this problem. So VIBG, violet, indigo, blue and green, they will undergo total internal reflection because their critical angle is less than the yellow's critical angle. So okay, so they will undergo total internal reflection. This orange and red, orange rest will undergo refraction. Okay, so total internal reflection two condition. One is denser to denser medium to rarer medium, and the critical angle should exceed the angle of incidence should exceed the critical angle. Okay, the beam of red light would undergo, no, this red won't undergo because their wavelength is after yellow. So only yellow critical, they are not changing the angle of incidence. So below this only will undergo total internal reflection. The red light would bend towards away from the normal. Denser to rarer means it should be away from the normal. This is also wrong. The beam of blue light would undergo, blue is below the yellow, so it will undergo total internal reflection. The beam of green lights would bend away from the normal. So here you see this there won't be no refraction. Okay, this total internal, that is a reflection, not refraction. Okay, the radius of curvature of a curved surface of the plano-convex lens. Plano-convex, one side is plane, other side is curved. Okay, one is flat surface and the other one is spherical surface. So it will convex irrespective of the side on which the object is. So the focal length won't change for this. Lens maker formula 6. So this is the lens maker formula. If you change R1 R2, then the focal length will not change. Okay, so this is the f dash equal to f. Here R1 plus 20 cm, R2 infinity, here R1 infinity, R2. So in both the cases the focal length won't change. Okay, acts as the irrespective of the side on which the object lies. Irrespective of the side is object lies. 40. So here this is the lens maker formula. Okay, the important thing here, this one you see here, this N1, this is the refractive index of the air. So if some other medium, you have to replace that formula with that instead of 1 and some other number. Okay, The phenomena involved the reflection of radio waves by the ionosphere is similar to ionosphere is less dense than the atmosphere. Ionosphere is above the atmosphere. The density of air decreases as we move towards the ionosphere. Okay, when moving towards the ionosphere, so the total from we are moving from denser to rarer medium. Okay, denser to rarer medium, total internal reflection of that air during the ambient range. Okay, okay, the direction of the ray of light incident on a concave mirror is shown by PQ. Okay, which direction in which the ray would travel after reflection by shown the four rays 1 2 3, which of the four rays, okay, correctly shows the, so this light is passing through the focus of the lens. So this is rule 3. Okay, so this way after passing through the it will go parallel. Okay, 4. The ray passing through the focus of the concave mirror or opposite pass through the director towards the focus in the reflected ray is parallel to the principal axis. That is important. Okay, focus is parallel to the principal axis. Reflected ray is parallel to the principal axis. This is 2. Okay, the optical density of the turpentine is higher than the water, while the mass density is lower. Figure 9. Okay, shows the layer of the turpentine floating over the water in the container. Okay, air, turpentine, water. For which one of the four rays incident on the turpentine, the path shown is correct. Okay, and the denser, we are moving from the denser to rarer. Okay, turpentine is higher than that of the water. Okay, denser to rarer we are moving, so this is away from the normal. 2, this is the away from the normal, this is the normal, and this is away from the normal. Okay, moving from turpentine, okay, water, this air, this is the normal, and this is away from the normal. Okay, this, so this is the correct one. Yeah, car is moving at the constant speed. Okay, straight road, looking into the rear view mirror. Okay, so you can go through. This is similar to the book problem. The side mirror, the speed of the approaching car would appear to increase as the distance between the car decreases. Okay, there are certain material developed in the nanoparticles which has a negative refracting index. The ray incidence from the air, medium 1 is air, into such a medium with such a medium means a medium with negative refractive index. Okay, shall follow the path is given by. Okay, see if you so the angle is measured, the anti-clockwise a positive angle, clockwise is a negative angle. So here the incident is positive, the refractive is negative. Actually, if you take the normal case that is given in this book, with a positive refractive index. See, this is with a positive refractive index. You see, this refraction is on the other side. Here you see this is with the positive interactive refractive index. Okay, that is on the other side, this angle, refractive angle. So this is the normal. Okay, other side of the normal, the incident ray this side is this is with the positive refractive index. But here with the negative refractive index, you see the refracted ray here, this side only. So here incident is positive, refract is negative. Okay, this is anti-clockwise is measured is positive, so this is the clockwise angle, so this is negative. So this is with the negative refractive index. Normally it will be this side, so in this case the refracted ray is this side. So here both positive. Okay, this is also anti-clockwise, this is also anti-clockwise. So this is not with the negative refractive index, this one is with the negative refractive index. Okay, here there is no refraction at all, there is only reflection. Consider a extended object immersed in water containing in a plane draw. When seen close to the edge of the draw, the object looks distorted. Okay, distorted due to the apparent depth of the points close to the edge is nearer to the surface of the water compared to the points away from it. This is one reason. The subtended angle, what is subtended angle is given in the book. The subtended angle of the object is smaller than the actual subtended angle. Some of the points of the object away from the edge are okay. These things okay. 9. So here you see the apparent depth and the real depth. So you see from here how it appears. Okay, real depth is the refractive index. Okay, then the other one is 21. What is subtended angle means? See here, this is the subtended angle from seen from the eye. The height is subtended angle. Okay, when subtended angle getting reduced, the image will get looks like a distorted. A rectangular block of this ABCD as a refractive index is given mu. A pin is placed midway on the face. Here this is a pin. Okay, when observed from the face AD, the pin, okay, appear near to A, not appear at all, because the total internal reflection when the incident exceeds the critical angle. Okay, the relation they are given the refractive index 1.6. Okay, there is a relation between the critical angle and refractive index. Sine of the critical angle is equal to 1 by refractive index. Okay, if you take refractive 1.6, then critical angle will become around 39 degrees. Okay, 39 degrees. So above 39 you will not see the pin at all, because there is all will be reflection, there is no refraction, internal reflection. So for this you will close to this A. The other case appear to be near A. 10. So this is the case when denser to rarer medium. Okay, so this refractive index is equal to 1 by sine of the critical angle. Denser to rarer medium in this case. Okay, then only total internal reflection also will takes place. Denser to rarer medium. Between the primary and secondary rainbow, there is a dark band known as electric dark band. Okay, they are giving this, telling the information. Between the primary and secondary rainbow, there is a dark band. Okay, you can read about this electron dark band. This is because light scattered from the region interfere destructively. Okay, this is the region. There is no light scattered in this region. Okay, so the angle made at the eye of the scatter with respect to the incident. Okay, this is also the correct. You can go through the details about the rainbows and this dark band. A magnifying glass is used as an object viewed can be brought closer to the eye than the normal near one. This results in the larger angle subtended by the object at eye. Okay, larger angle means more detail. Magnifying glass is more detail. Okay, formation of the virtual erect image. Okay, 22. More magnification. Okay, when focal length is less, then m will be more magnifying. Okay, less focal length, m will be more. The astronomical refractive telescope has the objective and focal length. Objective of the focal length FO 20 meter and the eyepiece of the focal length 2 centimeter. Okay, FO and FE is given. The length of the telescope tube is this. This we have to add these two, and the magnification is the ratio of the objective by the eyepiece. The image formed is inverted. Okay, 24, 25. This is for the telescope. For the telescope, this is the magnification. Okay, inverted image, it is forming the inverted image. See, this objective has a larger focal length than the eyepiece. Okay, this is important for the telescope. This is the magnification. Okay, this is the total focal length of the telescope, and we have to add both the eyepiece and the objective. Refractive index is inversely proportional to the wavelength and focal length. Okay, will the focal length of a lens for red light be more, same or less than the blue light? Okay, so more wavelength means more focal length. The wavelength, focal length is directly proportional to the wavelength. See, based on this formula, refractive index is inversely proportional to the focal length. Okay, focal length, refractive index more means focal length is less, and refractive index is inversely proportional to the wavelength also. So it is inversely proportional to the focal length and wavelength. That means these two are directly proportional. Focal length and the wavelength are directly proportional. So as the refractive index of the red is less than that of the blue, parallel beam of red. Okay, thus the focal length of the blue light will be smaller than the red. Okay, with GR, B comes before red, so the focal length is directly proportional to the wavelength. The near vision of average person is 25 centimeter to view the object with the angular magnification they have given. Angular magnification, that is the d by f. Magnification is 1 plus d by f, angular d by f. 10, what should be the power? Power equal to 1 by f. 18. Power they are asking is 1 by f, but they given the d 25 centimeter m, so d by f, m equal to d by f, then we can find the focal length 25 divided by the 10, they have given the angular magnification. So in this focal length it will be this, power is 1 by f, so this is 40 diopters, so this is the unit of the power. See, angular magnification, an asymmetrical double convex thin lens forms the image of the point of the axis. Will the position of the image will change if the lens is reversed? See, this lens maker formula, it won't change. Okay, if you interchange an object between R1 and R2. Okay, Q6, question number 6 I already showed you. See here, the radius of curvature of the curve is 20, the refractive index of the material lens in 1, so it will, so you can this irrespective of the side on which the object lies. Okay, this I already shown you, so you can refer to that. The immiscible liquids, okay, the density is given, refractive index, the height of the each is given. Okay, okay, this is due to the real depth and apparent depth. Real depth divided by the refractive index. Okay, apparent depth is real depth divided by the refractive index. We have to use that formula there. Okay, here, so here you can go through this answer. For a glass prism, okay, mu is refractive index given, the angle of the minimum deviation is equal to the angle of the prism, find the angle of the deviation. Okay, 20. See, this is the formula. Okay, you have to use this formula. At a minimum distance they given, this is the given. Okay, then after that they arrive this. Okay, see, these questions actually wherever show answer is that the answer is given in the answer, so you can go through it. So here a thin convex lens of the focal length is cut into the two pieces 0.5 centimeter above the principal axis. The top part is placed at 0, 0, that is important, 0, 0, and the object is placed at the this, find the coordinates of the image. See, the focal length is 25 centimeter. The object is placed in the twice the focal length, that the 2f, that is 50 centimeter length of the length. So the object is at 2f. Okay, 24. Okay, the object is at the 2f. So you use the lens formula, then you will get the image distance 50 centimeter. That means image is on the this side. So from here they have placed 0.5 above the principal axis. So the total distance will become the 1.5 plus 0.51. Minus 1.5. Okay, so the total it will be 1. This is the magnification factor. So this is the formula. So here see this object and the image will be formed here. Okay, only the distance will varies, and this is the scenario. Okay, these things also you go through the answers. See, important thing here in this ray diagram, some scenarios given in the book and some other scenarios you have to draw yourself based on the rules. Okay.